Okay, so today we are going to talk about section 9.5, the implicit function theorem. And the homework problem for these sections are, let me see, for the sections, okay, let me just assign a few more homework problems that I did not assign last time. That is that's number 16, number 21, and number 23. You only need to hand in number 16 and number 23. Okay, so let's first talk about the implicit function theorem. We would actually first state the theorem in two-dimensional case and prove it in two-dimensional case. The proof for the n-dimensional case, the more general case, is actually essentially the same. So let's say the theorem in two-dimensional. So we have f, which is a function defined on an open set in R2. So E in here is always open. And then we assume that they are continuous differentiable, continuously differentiable, so that this function is C1 on E. So this is a function, real value function. And we assume that AB is a point in E, and F at AB is 0. And the derivative, partial derivative of F with respect to X at AB is non-zero. Then the conclusion of the theorem is that first, there exists a neighborhood, open neighborhood. When I say neighborhood, I always say an open neighborhood U of AB in R2, and a neighborhood W of B in R, such that for any Y in W, there exists a unique X satisfying the following property. So that means that X and Y is in U, and F X Y is 0. So what it means is, I will explain it a little bit later. So this furthermore, if we write X equals to GY, this is unique, is in C1W, and the derivative of G is negative of the partial derivative with respect to X, the reciprocal of this, and the partial derivative times the partial derivative of f with respect to y, or this partial derivative actually, let me erase this. We would only emphasize that it evaluate at b. This is evaluate at a and b. So this is the theorem. Okay, so let's just, before we prove it, let's just try to understand what does it mean. So it means that suppose you have a function fxy, you have an equation fxy equals to 0. So suppose a and b are just a point of this solution, one solution. So this theorem tells us that if df dx, the partial derivative of this is non-zero, then we can solve this implicit equation. We can solve x in terms of y for any for xy near the point AB. Okay, so this is what the theorem tells us. Now let's think about this graphically. Say f x y equals to 0 is a level set. This is an equation. Now the gradient of this function is actually the normal direction. These are the gradient of the function. Is the normal direction. Now this theory, so the gradient is df dx df dy. So the theorem tells us that if the gradient of this is this first component is not 0, so that means that you have the gradient is have the x components, the horizontal component of the gradient is non-zero. Then near this piece, let's say this point here is AB, then the theorem tells us that near this piece, let me have the color. So near this point, you can find a piece here, so that this actually would define as the x would be defined. This would define a function x in terms of y. So that means that on any, in this case, in any, it would satisfy the horizontal line test because the function is x in terms of y. Now, so there are some points on this curve here that you may not be able to find a function, solve a function x in terms of y. Like these points here, you would not satisfy the horizontal line test when in this case these are the points where df dx equals to 0. This gradient has the x component equals to 0. The gradient is vertical. So this near here, you will not be able to find a function x in terms of y. Of course, you can find a function y in terms of x near these points, but not x in terms of y. So that is the statement of the theorem. So it's just about when you're given an equation like this, x squared plus y squared minus 1 equals to 0. We know that this the graph of this, of course, is the unit circle. We know that at this at any points you can always solve x in terms of y, but you would have positive, negative. This equals to 1 minus y squared. Now, however, at these 2 points here, you will not be able to solve x in terms of y. And that is because at these 2 points, df, this is our f, xy, df, dx, which is 2x, is 0 at these two points. So you cannot define x in terms of y. But you can this, of course, is you can define y in terms of x at these points. But except for these 2 points, you can so you cannot have x in terms of y. But except for these 2 points, then at any other point you can always find a neighborhood, so that you can define x in terms of y. So that is the statement of the implicit function theorem. Okay, so we are now going to prove it. So the idea of the proof is to reduce it to the inverse function theorem. All right. So the way we do it is that we define a function, a new function f. This I will call capital F. So this would be defined in this way. The first component is this smaller f. This is a real value function, a scalar value function, and y. Then so this would be a function that is defined on E, which is in R2, and the value would be in R2. Now, if we look at the derivative of this function at A and B this point, so this would be the matrix df dx at AB, df dy at AB, and then dy dx, which is 0, dy which is 1. So now we know that the determinant of this matrix at AB is just df dx at AB. That is not 0 by our assumption. All right. Now, then what it means is that we can apply the inverse function theorem. So that means so that would there exists a neighborhood U of AB and a neighborhood V of the image of AB, which is remember A and B, F AB is 0, so therefore this becomes 0B, such that F from U to V has an inverse, which we would call as G, back from V and U, and we because F is C1 function, and then we know that G is also C1 in V. Okay, so now we just need to use this conclusion, and then we already know what is U in this theorem. Let's go back to this theorem. So we need to find W. W actually is easy. and W, we just let W be the points of Y in R such that 0 Y is in U. Okay, so let's draw a graph here. So this is the I guess F is from okay. So okay, so this is the level sets of yeah, the point AB here. So this is let me change it. Okay. So this is E. This is a point AB. Now we just so we have a capital F, which map this to the point 0B, and we know that there's a neighborhood here, U, and there's a neighborhood here, V, so that this is F. The F is 1 to 1 and onto, and it has an inverse back G. All right. Now we let W. So what W is that we this would let X equals to 0. So this point here is I make mistake here. This should be V. This should be V. So W here is when X equals to 0. So this is W is this part. So this is X exit, this is Y exit. So when X equals to 0, then it's, so of course a W, you can, because V is open, you can easily see that W is also open. All right. Now we know that for any W in W, because this 0, that means that 0 in Y is in V. So we have a unique point. So you would have a function G 0Y would map back to the point where you still have Y here. We will call this point, this point is Y. This point we will call it as our little G Y. So remember this, we have this G is an inverse of F, so that would mean that capital F G 0Y, that is F G Y Y Y. X is 0. We know this equals to this Y, but this also equals to 0Y. So that would mean that F G Y Y equals to 0. So that means that this function X equals to GY is indeed a solution to this function, to this equation. So x equals to gy is solution. So that put the first part. Actually, we said we prove the existence part of the theorem. Now we want to prove that it is unique. And that uniqueness actually comes from the fact that f is 1-to-1. So unique. Yes. So that means that if you have 2x prime and not equals to x, and then so that f x y and then equals to 0 equals to f prime x y, then you would get a contradiction, because that means that this means that capital F at xy, which is going to be 0 fxy y, which this is 0 y, which is 0 y, and this is also the same as f prime fx prime y. So this would be a contradiction to because this, we know that contradicts to f is 1-to-1, 1-to-1 on e on u, because both x and y are in u. Both x, y are in u, and x prime, y prime are in u, by the assumption. So that means that this cannot happen. So this must be 1-to-1. So all right, we now prove that the first part. We just need to prove the fact that G is in C1 of W is coming from the fact that capital G X Y is in C1 of V. That is because this is G is just the first component, of capital G here. So that is why if this is C1, then this must be C1. And now to find the formula for the derivative of y, and then that is actually, remember that we have this equation, and then we just differentiate both sides with respect to differentiate both sides with respect to y, and then we are done. So that then this means we will have df dx times g prime y plus df dy equals to 0, and we evaluate at the point AB, then we would have g prime b equals to f dx at AB, and then df dy at AB. So that is the end of the proof of this theorem in 2-dimension case. Now, we can state this implicit theorem in higher dimension as well. So in order to to state the theorem in higher dimension, we first introduce, so this is the end, we first introduce some notation. So, we will let, in this section, we will let x, the vector x is actually has a vector in Rn. So it has n components, n coordinates, and then y would be a vector in y1, yn, m in Rm. Actually, I would write this, this is a transpose, I should write this as a column vector. Now, then x, y is a vector, column vector x1, xn, and y1, ym. I write the vectors as a column vector that is in Rn plus m. Now, the a function f is I have a vector xy is a function have from E. This is an open set in Rn plus m. So x is in Rn and y is in m. It's a function from Rn to Rn. So it has n components. Now, then the derivative, the total derivative of this function is then this is so this is df1. It has n components, so df1 dx1, and then df1 dxn, and then we now start with df1 dy1 and df1 dym. So, and then you have dfn dx1 dfn dxn and dfn dy1 and dfn. Okay, so this does not look good. dfn dym. So this first n column, we will call it as df dx. So this is the first, and then the last m column we will call it df. So dy. So therefore, this matrix, this total derivative, we decompose into the first matrix here. This is n by n, and this is n by m, and this matrix here is n by n plus m. All right. Okay, so now with this notation, we can say the theorem. We will call it as a theorem 1 prime is, again, a more general form of the implicit function theorem. Okay, so the theorem says that suppose you have f, which is from E n plus m to Rn. This is an open set. So, and then we assume that this is C1 on E. So that means that it has all continuous first order partial derivatives. We assume that AB is a vector in Rn plus M. So the first this component is in Rn, and the second component is in Rm. Then and then we assume that this map A B equals to 0. However, the partial derivative total partial derivative at this point is invertible. So that means that this matrix here is invertible. This n by n matrix here is invertible. So that would mean that now in this system of equation, you can solve the x in terms of the y's. Then there exists a U neighborhood of AB and W a neighborhood. This is in Rn. This is an open set in Rn plus M, and this is a neighborhood of B, which is an open set, an open set in Rn, such that for any x, for any y in W, there exists a unique x such that xy is in U, and f xy is 0, and the point G, if we write if we write x as equals to gy, because it's unique, so you define a function, then g is C1 in W, and the derivative, the total derivative of G and B is the negative of the inverse of the total partial derivative with respect to x, the inverse. This is an n by n matrix, okay, and times df dy at AB. So at the end, this is n by n. This matrix here is n by m. So this matrix here is n by m matrix. And this is the implicit function theorem. The proof actually is identical to what I give in the special case where both n where both n and m are 1. So in the two-dimensional case, so I will skip the proof here. Instead, we are going to look at an example, a very simple example here. So this example. Now, so suppose we have f have two variable x here, y here. So it is defined with this formula 2ex1 plus x2 y1 minus 4y2 cosine x1 minus 6x1 plus 2y1 minus y3. So this is a function defined x we have x has 2 variables, y has 3 variables from R2 plus 3. It has 2 components, so R2. So this is our F1. This is our F2. Now, if you look at the total derivative, first at all, you know that if we let A equals to 0, 1, and B equals to 3, 2, 7, and you compute this A, B, so okay, let's just compute one of them. X1 is 0, so this is 2, and this is x2 is so this is plus 3, and this minus of y2 is 8, and then plus 3, so this term is 0. Then if you plug this x2 is 1 and x1 is 0, so therefore is 1 minus x1 is 0, so this 0. X2 is y1 is 3, so this is 6, and y3 is 7, so therefore this is also 0. So this map to the point 0, 0. All right, and then if we look at the partial derivative, we look at the total derivative of f. So then let's just okay, let me just, so this would be a huge matrix. So this df1, let me just calculate some of the term, df1 dx. So this partial derivative with respect to x1, and then df1 dx2 and df1 dy1 df1 dy2 and df1 dy3, and you do the same thing for f2, dx2 df2 dy1 df2 dy2 and df2 dy3. Let's just calculate some of the terms. This is a simple computer. df1 dy1. Okay, so this is d2x1. That is all. And df1 dx2, which will give us y1, and df1 dy1 would give us x2, df1 dy2 would give us -4, df1 dy3 would give us 0. Okay, so you can find the other terms as well. And then if you evaluate this at the point A, B, and then you can find that derivative at the point A, B. You can find this is a matrix, and it is this is give us 2, this give us a 3, this give us x2 is what x2 is 1, and that gives us -4. This gives us 0, and likewise you can do a computation. This would give us -6, 1, 2, 0, -1. Okay, so this part is df dx at the point AB, and this part here is df dy at the point AB. Now, you can see that the determinant of this point is determinant of df dx at the point AB is 2 plus 18, so it's 20, it's not 0. So therefore, this matrix is invertible. So that means that we can solve we can we can solve x equals to gy for near the point A, B. We can solve the equation. Okay, maybe I should say solve. Let me rephrase what I said. So therefore, f x y 0 has a solution, has unique solution. This is the solution near this point. Now the total derivative of this function at the point B is then given by negative of df dx at AB, the inverse, times df dy at AB. Now this is a 2 by 2 matrix, so therefore its inverse is just you have the determinant, and then you exchange these two, so it become 1, 2, and you keep you change the sign of these two, so it become negative 3, 6, and then you multiply df dy, which is this matrix, so it's 1, negative 4, 0, 2, 0, negative 1, and you do the computation, and then eventually you get the this answer, 1/5 and negative 3, 20, and negative 1/2, 6, 5, I mean 6/5 and 1/10. So this is the derivative of the solution, x equals to gy. That's the derivative at B, at the point B, and that is at the end of this example. Okay, let me make a remark that in this book and in this lecture, we actually in the previous section we put the inverse function theorem, and then we use it to prove the implicit function theorem. Implicit function theorem. These two theorems essentially are equivalent. That means that if you know how to prove one, and then you can actually use it to prove the other. So you are an exercise I want you to just think about yourself is how about if you assume the implicit function theorem, can you come back to prove the inverse function theorem? So remember when we proved the inverse function theorem was quite involved, and we have to use the contraction principle. We have to construct, use kind of a Newton's method and construct a function map, and then to use the contraction principle. Okay, so this is the end of this section.